Greetings and welcome back. Today we'll be looking at specifically carbon-13 NMR. So going back a little bit, we have used hydrogen NMR for spectroscopy in order to try to identify an unknown sample. Hydrogen NMR can give you, in general, a lot more information about a molecule than carbon-13 NMR is. So right off the bat, I want to let you know that hydrogen NMR is generally more useful, especially for simple experiments where you're just looking at one by itself. Carbon-13 NMR gives you a lot less information, and therefore, while it is useful, it is more often used in more complicated experiments and less often used for standard, straightforward small molecule spectroscopy. So for the sake of this class, we're just going to consider the very basics of carbon-13 NMR, which are in general less often used because they're in general less useful than hydrogen NMR. But that being said, my main goal for you with carbon-13 NMR is to be able to match up a spectrum from a carbon-13 NMR to a sample to tell me, could these things possibly go together or not? All right, so part of the problem with carbon-13 is that carbon-13 is not a very large, or doesn't represent very many carbons. Hydrogen, which has an odd molecular mass, H1, H1 shows up about 99% of the time when we're looking at hydrogen. So of the hydrogens that exist, approximately 99% of them are H1, and they have an odd mass and are therefore, they have an atomic spin and they show up in the NMR. Carbon-13 only represents approximately 1% of the natural abundance of carbon. And therefore, when we are looking for carbons in the carbon NMR, we can only see 1% of the carbons that exist. So therefore, there's not a lot of carbons to see. So what we do see gives us a little bit less information than we could see with hydrogen. So let's move in and see how this makes sense and what information we can tease out of a carbon NMR. So once again, I'm going to go back a second and say that for hydrogen NMR, the information that we could glean was, number one, how many environments. Number two, we could tell the chemical shift, and that is just in ppm. Number three, we could tell information about how many hydrogens were in that environment based on the integral. And number four, we could tell information about the neighbors based on the splitting. All right, for carbon-13 NMR, we can, in the same way, tell the number of environment based on the number of peaks, and we can also tell information from the ppm or the chemical shift. And that's it. There are not integrals that we can use, and the splitting is not very helpful. And so, in fact, usually what we do is just completely turn splitting off. There are reasons for that we can get into if you'd like to know, but for our specifics, these are the only two things we're looking at. And these are two of the more simple things about NMR. So essentially, carbon NMR is a much more simple spectra. It doesn't tell you as much information, which makes it easier to understand because it's not telling you as much. So here's what we're looking for. The number of environments in carbon NMR is exactly the same as the number of environments in the hydrogen NMR. That is to say, you're just basically counting the number of carbons that are showing up. So in the sake of this molecule right here, when we did hydrogen NMR, we would draw in all of the hydrogens and we would count out how many environments there are. We would label them A, B, C, D, etc. In the case of carbon NMR, we would do the same thing, except we don't need to draw out the hydrogens because we're not looking at hydrogens anymore. So we would see environment A, environment B, and this carbon right here, which doesn't have any hydrogens, would be environment C, and then both of these guys would be identical, so they would be environment D. So we would see that we have 4 different signals from this. So that's something to keep in mind. If you have something like this guy, this would give us only 2 signals, or excuse me, this would give us only 1 signal in hydrogen NMR, but because that guy right here is definitely a carbon, we would see 2 signals in the carbon NMR. So you're just looking for the number of carbon environments. That often by itself is can be very helpful information, especially if based on hydrogen NMR you limit it down to a couple different possibilities. Carbon NMR can often easily figure that out for you. All right, so the other thing we can look at is the chemical shift. In general, I'm going to break this down into kind of these simple categories. sp3 carbons usually appear somewhere between 0 and 35 ppm. So the scale for this is much higher. It's no longer 0 to 12, it's about 0 to somewhere around 200 plus. This is the ppm in terms of chemical shift. Or I should say the chemical shift in terms of ppm. All right, so the second kind of thing we look at is sp3 carbons attached to halogens, and those are usually between about 30 and 60 ppm. So they've been shifted up about 30 from where the generic sp3s would show up. An sp3 carbon attached to an oxygen appears next, a little bit higher, show around 60 to 90 ppm, which would be approximately 60 higher than normal. And that's really all we look at, is just a carbon that's by itself or next to a halogen or next to an oxygen. sp carbon triple bond carbon comes next. Those guys show up usually around 75 to 100 ppm. The sp2s are the highest, and the sp2s show up first. The carbon double bond carbon shows up between usually about 100 and 150 ppm. And then highest of all is the sp2c double bond O, which shows up between approximately 150 or 160 and 210 ppm. So they're much higher. So the order that we're looking at is actually kind of similar to how it was for hydrogen NMR. These right here, these carbons, right in here, you can consider these guys to just be the generic CHs. So those are like 1 to 1.5 ppm for hydrogen. For just kind of generic carbons that are in alkane chains, they're at the lowest amount, usually 0 to about 35. Next comes carbons attached to halogens, and carbons attached to oxygens, and then carbons in triple bonds, finally carbons in double bonds to carbon, and then double bonds to oxygen. And so that's all we're really looking for in here. So we would predict that this carbon in environment A would show up in that 0 to 35. The guy in environment B would also be in that 0 to 35. The guy in environment C is right next to a chlorine, so that should show up somewhere in this 30 to 60 region. And then the carbons in environment D would show up somewhere in that 0 to 35. So this is all that we would be able to tease out about this, is that in the NMR of this molecule, we would see 4 peaks. 3 of them would be between 0 and 35. 1 of them would be between 30 and 60. So let me grab the carbon NMR of this guy. So you can see from that carbon NMR that things are a little bit higher than we predicted, but that's okay. They're in those rough regions. So you can see that environment C is right here. Oh, that doesn't show up very well. Let's try pink. So environment C is right there. That's the carbon that's directly next to the chlorine. It's showing up around 70, so it's a little bit higher than 30 to 60, but kind of in that rough region. Probably those 2 peaks in the middle there, the one that is somewhere around 30 and the one that's a little shy of 40, those are the ones B and D most likely that are a little bit further away. I don't know which is which, but we'll just put B/D because those are the 2. And then A is furthest away from the chlorine, so that's most likely this guy over here. And so it proceeds a lot like hydrogen NMR, where if they're kind of close to a chlorine or kind of close to an oxygen, they end up being a little bit higher. But we can't do any integrals with this, and you'll see that they're all just going to be singlets in the most common carbon NMR experiments. Therefore, there's no splitting to worry about or anything like that. So really all we're looking for is the number of environments and roughly where they show up in terms of ppm. So I'm going to give you a couple quick examples. The first one will be this molecule right here, OH, the cyclohexene, with a little methyl group coming off. All right, so first question I would like you to answer is, how many environments would that molecule have? And hopefully you got that right, but we would see that all of those carbons are different and that there are 7 of them. So we could label these out A, B, C, D, E, F, G, because there's not a lot that we can do with these guys besides try to imagine where their chemical shifts might show up. That's about it. I mean, we can put those letters on there, but there's no shifting or no integrals to figure out and no splitting to figure out, so it's a little bit more simple and pretty dry, I would say. But we would expect B and C, which are both in sp2 carbons, these guys are in those carbon double bond carbon region, to show up somewhere between maybe 100 and 150 ppm. And this environment D that's right next to the OH, we would predict somewhere between 60 and 90 ppm. And all of the other ones should be somewhere in the range of 0 to 35. All right, so let's see how we did. And there we go. We see two of them between 120 and 140, so those are definitely environments C and B, or B and C. And then we have one all by itself down here. This is environment D. And then all of the other ones are just in this group down here. They appear somewhere between about 20 and 35, something like that. So this would be kind of how to take a molecule and turn it into a spectrum. But taking a molecule and turning it into a spectrum is not what I'm going to ask you to be able to do. In general, what I'm going to ask you to do is I'm going to give you a spectra and say which of these molecules might fit this, or would this molecule fit or not. So let's try that. So here we see a carbon NMR and a molecule. So my question to you is, could this molecule and this NMR possibly be together? In other words, could this molecule give that carbon NMR? So see if you can answer this. And yes, this is definitely a possible match. So we could see that this guy right here has 1, 2, 3, 4. Don't forget that that's a carbon in there. 5, 6 different environments. And the one up at the top has 6 different peaks, so that seems to work out pretty well. Our highest should definitely be this environment D right here, because that is a C double bond O. C double bond O's are the highest that we will see in terms of carbons. We said that those show up somewhere between 150, 160 and 210, and we definitely have one peak way up there. And so that is, most likely your peak D right there. So that makes sense. The only other one that should be kind of above our baseline simple alkane region is this one right here, environment E. That's a carbon directly next to an oxygen, so that one should be somewhere in that 60 to 90 region. And you can see that indeed we do have one in the 60 to 90 region, and then everything else is clustered down in those kind of basic regions. And we have 4 peaks there. We would have 1, 2, 3, 4 other things to take care of. So this is definitely a possible match. Hopefully you can see how straightforward that is. In this case, we might not need that. We could probably figure out the identity of this molecule using hydrogen NMR, but it could serve as a confirmation. It doesn't take that long to run a carbon NMR. So it can be helpful. All right, here's a carbon NMR. You can see that it has 5 peaks, one around 180 and 4 of them down kind of below 35 or so. I'm going to give you 4 molecules and ask you which one could possibly be accounted for in this NMR. So the very first thing I would do when trying to see which of these possibilities in terms of molecules matches that NMR is to go through and count the number of environments. It's the simplest thing to do. So in the NMR itself, we have 5 environments. And that's as simple as counting the number of peaks. All right, and so when we go through these carbon NMRs, or these molecules, we would do the same thing. So starting in the top left, we have 5 environments for this one. Don't forget to count the carbon and the carbonyl. So that's 5. All right, the one over here, both of those guys should both be A, B, C, D. So this one only has 4 environments. So right off the bat, you can say that that one is not a possibility. All right, down here, this guy should also have 5 environments because all of those carbons are different. And looking at the bottom right, we have 5 carbons in a 6-membered ring. One of the members in the ring is an oxygen. So A, B, C, D, E. And so that guy also has 5 environments. All right, so at that point, we can't cross anything out. All right, so let's look at what we have up here in terms of chemical shift, because that'll let us sort it out. That's the other thing we can consider. This guy has 1 in that carbonyl region. So the carbonyl region is the highest. It's between 160 and 210. So we definitely have a carbon in the carbonyl region, and we have no other carbons that are attached to anything else of any significance. So we can see that, let's go down here to the bottom. This alkene right here, it has no carbonyls. It has two guys that are in the C double bond C region. So you should see in this molecule for this NMR that we would have two carbons that are between approximately 100 and 150, and we have none. So this is definitely not a match. But both of these guys have carbons in a carbonyl and four other carbons. So to tease this out, we would see that in this guy A, B, C, and D are not next to anything. So therefore this guy is a possibility. But when we come down here to the one on the bottom right, environment A, oh dear, environment A is right next to an O. So therefore environment A should be showing up between 60 and 90. And this guy does not have any peaks in that 60 to 90 region, so we know that that's not a match either. So I would just consider, this is what I'm going to ask you to do, is given a spectrum to either match it to one of a possible list of molecules, or to just confirm whether or not a molecule matches to a spectrum. All right, thank you very much. Please bring any further questions you have to class. Otherwise, we will practice when we get there. And have a great day.